You can review content from Crash Course Organic Chemistry with the Crash Course app, available now for Android and iOS devices.
Hi, I'm Deboki Chakravarti, and welcome to Crash Course Organic Chemistry. The term organic chemistry was first used to describe molecules isolated from living things. This was back in the 1800s, when some scientists thought that organic compounds had to be made biologically. But in the past 47 episodes, we've seen plenty of examples of human-made chemicals, like polymers and medicines. We explored some of the lab techniques and equipment that let us make new chemicals, and even worked through multi-step organic syntheses. Despite all that, living things are arguably the best synthetic chemists, carrying out countless simultaneous organic reactions at mind-boggling speeds. So in this episode, we'll return to organic chemistry's origins to explore the chemical building blocks of life. The organic chemicals that make up living things can be organized into 4 classes: carbohydrates, nucleic acids, lipids, and proteins. Carbohydrates can be sweet, like the table sugar we put in tea, but all the nomenclature might make you a little sour. So let's get that out of the way first. Most carbohydrates are molecules with this general formula. There's usually a 2-to-1 ratio of hydrogen atoms to oxygen, and the number of carbon atoms, the M subscript, ranges from 3 to 9. One way to refer to carbohydrates is by the number of carbons they contain. A carbohydrate with 3 carbon atoms is a triose, 4 a tetrose, 5 a pentose, 6 a hexose, and so on. We can also classify carbohydrates based on their functional group, because they're either aldehydes or ketones. Of the trioses, glyceraldehyde is an aldose because it contains an aldehyde, and dihydroxyacetone is a ketose with that ketone on the central carbon. 5-carbon pentoses and 6-carbon hexoses mainly exist as cyclic hemiacetals in solution. As a reminder, hemiacetals form when one alcohol group adds to an aldehyde or ketone, and usually the equilibrium favors the aldehyde or ketone. But 5- and 6-membered ring hemiacetals are often more stable than the open chain forms. We saw this with glucose in episode 29. This 6-membered ring form of a sugar is called a pyranose, named after the pyrin ring, which looks like this. Sugars can also form 5-membered furanose rings. We met tetrahydrofuran in episode 28 as a good solvent for Grignard reactions. A really important carbohydrate that forms a furanose as its cyclic form is ribose, which we'll see again in nucleic acids. These linear representations of carbohydrates are called Fischer projections. Sometimes all the carbon atoms are drawn out, and sometimes carbons are just shown as crossing lines. And you can also show stereochemistry if you want. See, all of the horizontal bonds are coming out of the screen toward us. Fischer projections are drawn so the highest priority group is closest to the top of the diagram, the aldehyde of an aldose or the ketone of a ketose. Then the H and OH groups are placed on specific sides of the chiral carbons. If I build this with a model kit and point all of the horizontal bonds toward me, the carbon backbone starts to curl around to form a ring. The structure isn't actually linear. So even though it's a linear representation, we can use the Fischer projection to draw cyclic structures too. Before we start drawing rings though, there's one more nomenclature thing to learn. If the OH group on the bottommost chiral carbon of the Fischer projection is on the right, it's a D sugar with a capital D. And if it's on the left, it's an L sugar. This D and L designation is named for the Latin dexter and laevus, right and left. So to sum all this nomenclature up, this ribose molecule is a pentose because it has a 5-carbon chain, an aldose because there's an aldehyde on the top, and a D sugar because the OH group on the bottommost chiral carbon is on the right. Sweet. To really understand carbohydrate rings, let's do a quick chirality review. When a nucleophile attacks an aldehyde and a chiral carbon forms, it can attack either face of the trigonal planar aldehyde. In this simple example, if methoxide attacks from the front face, the alcohol gets pushed back into the screen. But if methoxide attacks the back face, coming from behind the screen, the alcohol gets pushed toward us. This is how we get a mixture of stereoisomers at the anomeric carbon in a carbohydrate ring. The anomeric carbon was the carbonyl carbon and becomes sp3 hybridized when the linear carbohydrate closes to form a ring. We can show the ring closure on a Fischer projection by drawing a long bond from the highest number chiral carbon to the anomeric carbon. Our new OH group can be on either side of the Fischer projection. A stable 5-membered ribose ring forms when the D or L determining hydroxyl group forms a hemiacetal with the aldehyde at carbon 1. And to draw the ring form, we use a diagram called a Haworth projection. To start, we draw a 5-membered ring and put the oxygen right at the top. Now we need to look at the hydroxyl group attached to the highest numbered chiral carbon again, the one that makes it a D sugar or L sugar. This is the OH group that ends up in the ring, and it'll determine where the CH2OH group points on the Haworth. If it's a D sugar and the OH is on the right, the CH2OH points up. That's what we have here. If it's the less common L sugar and OH is on the left, the CH2OH points down. And remember, we don't have to write CH2OH every time. We can represent the carbon as a bent line, draw the hydroxyl group, and leave the 2 hydrogens off because they're implied. Much neater. Now we've got to sprinkle in the rest of the OH groups. The groups on the right in the Fischer projection point down, below the ring, on the Haworth projection. And the groups on the left in the Fischer point up on the Haworth. The drawings of alpha and beta ribose rings look slightly different. In an alpha ribose, our new OH group and this CH2OH group are on opposite sides of the ring, away from each other. And in a beta ribose, the groups are on the same side of the ring or by each other. And we're done. Ribose is an important pentose, but these 4 carbohydrates are the most abundant hexoses in nature. Glucose, galactose, and mannose all form 6-membered pyranose rings as their most stable structure, while fructose usually forms a 5-membered furanose ring. Let's practice by drawing a Haworth projection of alpha-D-glucose. We need to start with a 6-membered ring this time, and we place the oxygen atom in the upper right. And let's number our carbons. As before, the highest number chiral carbon determines if the carbohydrate is D or L. It's on the right, so this is another D sugar, and the CH2OH group points above the ring. Let's put it there and simplify the drawing. Let's begin with carbon 2 to add the hydroxyl groups. Those on the right of the Fischer projection point down on the Haworth and vice versa. Lastly, we just have to make sure it's the alpha form. So we'll make the hydroxyl on carbon 1 point away from this group coming off of carbon 5. And that's it. Since the Haworth shows groups that are above and below the ring, it maps really well onto the chair form. We place the substituents that point up on the Haworth in the positions on the chair that point above the ring. Like I mentioned, this is the D form of glucose, but let's look at alpha L-glucose for practice. The CH2OH group points below the ring on the Haworth projection, and the stereochemistry of all the carbons are flipped. L-glucose is the enantiomer of D-glucose. And here's what its Fischer projection looks like. That's all for carbohydrates for now. On to nucleic acids. We briefly mentioned these structures in episode 42. The 2 DNA bases that link up because of a sun-caused paracyclic reaction. Both DNA and the closely related RNA are nucleic acids. One building block is a nitrogenous base, which is a nitrogen heterocycle, a ring with more than one type of atom. These are categorized as single ring structures called pyrimidines or double ring structures called purines. The pattern of double bonds in nitrogenous bases doesn't exactly match the chemicals pyrimidine and purine, because added groups can cause different tautomers of the structure to be favored. Remember, tautomers have different positions for double bonds and hydrogen atoms. As we saw way back in episode 4, these tautomeric forms are what made it so hard to initially figure out DNA structure. In DNA, the NH groups of these bases link up with the anomeric carbon of a 2-deoxyribose sugar in a dehydration reaction. The deoxy in the name means there's no hydroxyl group on carbon 2 of ribose. A nitrogenous base connected to a carbohydrate is called a nucleoside. I remember this has an S because it's just the sugar. Add a phosphate group and we get a nucleotide. I remember this has a T for total. This unit is the whole building block for DNA and RNA too. Like we mentioned, DNA uses deoxyribose as its sugar. That's why it's called DNA, for deoxyribonucleic acid. But in RNA, the sugar is just ribose, with the OH at the 2 position of the carbohydrate. It's short for ribonucleic acid, and the nitrogenous base uracil replaces thymine. That's it for now, but we'll revisit nucleic acids next episode and see how they link up to form polymers and carry genetic messages. Next, we have lipids, our hydrophobic class of building blocks. They're made up of hydrocarbons with just a few polar groups. We've met a few examples in the series, like cholesterol, the sex hormone progesterone, and vitamin D. In episode 31, we touched on fatty acids, which are carboxylic acids attached to long hydrocarbon chains. They're pretty straightforward to draw, especially compared to some of the rings we've been dealing with. They can be saturated, which means they have no double bonds, or unsaturated with double bonds. When fatty acids link up to a molecule of glycerol, we get triacylglycerols or triglycerides. These are the main form of fat we consume and also how we store it in our bodies. We can replace one of the fatty acid chains in a triglyceride with a phosphate group to get a phospholipid, which is a component of cell membranes. This phosphate at an end carbon of the glycerol can be attached to a whole variety of R groups, depending on what types of cell the membrane belongs to. Okay, really briefly, we've got one final building block to go. Amino acids contain an amine and a carboxylic acid, both connected to a central carbon atom, the alpha carbon. The alpha carbon also has a variable R group sticking out called a side chain. Each of the 20 standard amino acids has its own unique side chain. There's some interesting stuff going on within an amino acid molecule. Our blood and cells are slightly basic environments, above the pKa of a carboxylic acid, but below the pKa of the protonated amine. This causes the carboxylic acid to lose a proton, which the amine generously accepts because of its basicity. This proton exchange creates both a positive and negative charge in the amino acid molecule, called a Zwitter ion. This whole becoming charged thing can also happen with side chains that contain carboxylic acids or amines. In fact, we can classify the amino acids into 4 major groups based on their side chain properties. As we'll see in the next 2 episodes, amino acids determine the shape of a protein, and some side chains even let proteins cause chemical reactions. But that's it for now. In this episode, we converted between Fischer and Haworth projections of carbohydrates, linked nitrogenous bases, sugars, and phosphate groups to form the building blocks of DNA and RNA, reviewed lipid structures, and saw that amino acids form Zwitter ions and have side chains with specific properties. In the next episode, we'll join these building blocks together and take a closer look at biological polymers. Until then, thanks for watching this episode of Crash Course Organic Chemistry. If you want to help keep all Crash Course free for everybody forever, you can join our community on Patreon.